All right, welcome back. This is a lecture on expectation, variance, bias, variance trade-off. So I'm Professor Wu. Let's get started. So the population of the United States is approximately 15 million people as of 2013. Now, if we want to find the average height, we know how to find the average. So if we want to find the average height, we could have just take the entire 315 million people and just average it together. And this right here is the equation for average. You will sum everybody up and divide by the total number. So the average of the total population is called the mean, also known as the expectation. You can write it this way. Okay. And the equation looks something like this, where you count through every single person and get the height, and then you sum it up and then you average it. Okay. Now, in a sentence, we will essentially say that given x, which is the population height, the expectation of x is 5 feet 4 inches. Okay, so that's how we would say the expectation. Now, getting the height of every single person out of 315 million is a lot. And if you have limited resources, instead of trying to get the height of everybody, we tend to sample them. We just got a subset of the people, let's say 10,000 people. And with 10,000 people, we only have to collect the data for 10,000 and average their height together. And the idea is that if the sample size is sufficiently big, it's big enough, then the approximation using 10,000 should be relatively close to the whole population. That's the idea. Okay. So, where the whole population is called the expectation or the mean, and if you only have subset, it's called the empirical mean. So, they're both means when you find the average. One is called just the mean, other one is called the empirical mean when you only have a subset of the population. So, why can we, like, how do we know that that is true? Why can we just take only a subset of the total population and use that to approximate the height of the total population? So if this is the total population, how do we know that we can just take a small subset of it and it will be representative of the larger set? Well, it's the reason why we know that is through this thing called the law of large numbers. Let's say I define a bunch of samples we collect. We collect n of them, so the first, second, all the way to the nth person, and then we calculate the average. All right, so this is the empirical average because you're not taking the total, you're taking a subset. So with this average, the law of large numbers basically says that given mu as the true average. This is true average, and this is your predicted average. So the difference between predicted average and the true average is called the error. So the law of large number says that the probability that the error is bigger than some tiny number epsilon. So this is a small number, right? As long as it's not zero, it's just tiny. The probability that the error is greater than some tiny number is equal to zero as you increase the sample towards infinity. So as you have more and more sample, the probability that the error will be big is essentially zero. That's why we know that out of the total population, if you get a big enough subset, the error between them approaches zero. Okay, so that's the reason why very often out of the whole population we don't take data of the whole population. We take a subset, and then it allows us to save a lot on computational power. Okay, all right, let's move on to these concepts. So we use the word mean, expectation, variance, average, and if you have taken probability and statistics, all of these concepts should be pretty easy to, like, should be familiar with you. So so this is really a review, but hopefully we will go through the reason behind the equations better and you will be able to understand them. So average. versus expectation. We are all familiar with the concept of average, right? You know how to average a bunch of numbers together. So, given four numbers, 1, 2, 2, 3, the average can be simply calculated using the equation we talked about. You add up all the samples and then divide it by the total number of samples. So that's like averaging. So you would add up 1, 2, 2, 3 and divide by the total number of samples, which in this is 4. Now, when we do perform average using this equation, there's actually a underlying hidden assumption. And the hidden assumption is that this equation is that the value of 1, 2, 2, 3 are all equally likely of 1/4. So we're equally likely to get this because 1/4, 1/4, 1/4, 1/4. So the other way to write the same equation, so this is the average. That was the original perspective and the way most people understand average. The alternative perspective is to say that you got one and that was 1/4, 1/4 of the total, right? So 1/4 you got a one, 1/4 you got a two, 1/4 you got a two again, and 1/4 you got a three. So these two perspectives, like the equation and the result, are the same, are mathematically the same. However, looking at them this way versus this way, these two are different perspectives completely. The two equations are not really different. However, they present a different way of looking at averages. Okay, so so let's say we combine these two events because that's two. Therefore, the probability that two will happen is 2/4, right? So if we just add them together, then we can rewrite the average equation in terms of the perspective of the probability, which looks like this: one, that's the event. The probability that one happened is 1/4, and then two, the probability that two happened is 2/4 because you saw it twice. And then three, the probability that three happened is 1/4, leading us to a different equation, which we loop through each possibility. We loop through each possibility, multiplying by the probability of it happening. Now, take a second, notice the difference between equation 1 and equation 2. They both find the average. However, this right here, this perspective, you are looking at the possible events rather than at the samples. So here are all the possible samples, like 1, 2, 2, 3. Here, you're only looking at the events, which 1, 2, 3. There's no repeat. And you are multiplying by its associated probability. And that leads us to a different way of calculating average and mean. And this perspective is much more powerful, especially when you only have probability. So this tells us that we have two ways to essentially calculate the average. The traditional perspective that most of you are probably familiar with, which is this equation, and the probabilistic perspective, where we look at each event and the probability associated with the event, and they calculate the same thing. They calculate the same thing. Okay, so we're going to refer to the probabilistic perspective here, the expectation. So when we talk about expectation, average, this notation is what you should pay attention to. And that over here, you have the two ways of calculating expectation. If you only have the samples, you can just average them together. If you have the probability of each event, you can use this equation. Okay, it's very important that you distinguish the two possibilities of calculating average. The first is if you have raw data, right? If you just have data, of course you can get the probability out of it, but with the raw data, you can just calculate the average, just add them together, right? And the other time, we have the events, 1, 2, 3. And with these three events, we know the associated probability. Therefore, the equation to calculate the average is you loop through each event, 1, 2, 3, here, and then multiply by the associated probability. Okay, let's take a second, see if you can take a moment and calculate the expectation for this data set here. Okay, pause the video, we'll move on. The solution is here. All right, So, like I said, there's different forms of writing expectation and mean. If we're working with the entire population, we call it mean. Also, we call it expectation. We symbolize it with the symbol mu. Okay, mu, or we write it this way. They're the same thing. And if it's a discrete amount of data, then you would do it this way. This is the equation. However, if it's continuous, instead of summation, you need to deal with an integration. Okay. Now, example of continuous distribution, like if you want to find the average location where the MBTA red line will break down. So that's a concept of distance, hence is continuous. Or discrete is what's the average value or expected value you will roll for a die. Okay. If we're working, so this right here is if we're working for the entire population. But if we're working with a subset of the population, we also call it empirical mean and expectation. But the symbol we use is x bar. Okay? X bar. You can also write expectation of x, but we prefer x bar. That way you can distinguish mu and x bar, whether we're talking about the total population or a subset of the population. All right, now you want to pause the video and see if you can mentally consolidate the idea of expectation. So, see if you can go from this equation, think through everything we talked about, and see if you can arrive to the probabilistic perspective of expectation. Okay, pause the video. We're going to go on. All right, so here's your next given the probability distribution. So the probability distribution goes from here. Well, it goes from 0 to 1.5, which is here. So the distribution looks like this. So this is the distribution, and everywhere else is 0. Okay, so it goes like this. So that's the probability distribution. I want you to take up Python and see if you can calculate the expectation. Okay, so this is remember with Python, you can find the integral, right? So you to find the expectation continuously, then you need to take this integral. Okay, so you can do. You don't want to do it by hand. You could, but pull out Python and use the quad function. All right, pause. We're gonna go on. Here is the solution. So hopefully you got it. Okay, we have now learned the equation for expectation as this, right? So this is the probabilistic perspective. The the expected value tells us the most likely event that will happen, right? The expected value tells us the most likely value. However, sometimes we don't want to know the most expected value. We wanted to know the most expected function over value. In those cases, when we instead of x here, we put if we are looking for a function of a value, we will put a function here. I'll give you an example. What when in under what cases? Sometimes we don't want to know the most likely x. We want to know the most the expected the average distance from the center. So we want to average the distance from the center instead of averaging the x, right? So in that case, one second. Okay, in that case, this right here, you have f of x and you find the average. Notice how this part goes right here. Right. Practice this idea and see if you can find the expectation of f of x given x as this. Okay. We'll go on from here.